So, welcome to my dear students. Today we are going to discuss about a very important feature of microcontroller that is called PWM. So already we learned about interrupt. So we will be generating the PWM with the help of interrupt and timer. So that I will elaborate very slowly. One kind of PWM is required for, that is, just you define a duty cycle, it will keep on continue with that duty cycle. Another is called sine PWM, which is very much important for inverter switching. So these are the two things we will learn today. So first, I will go for the code. So this is the, already you are familiar with the embedded coding. This is the general structure. Shortly, I will start one course on DS PIC. It's a PIC controller. Same, this microchip technology. There also you will, if you join there, you will understand the similarity. The register names will be slightly different, but all the functions are same, more or less same. Slight difference will be there. So, as I told, this is the header file inclusion. These two header files will be needed here for the program. And here is the place for a global variable declaration. One function I have defined here, pin configuration. Already you know, the pin configuration means it will define whether the pin will be served as input or output, for that only. So here we are using B port, and here you see this PB1 and PB2. These two I made as one, so that will work as output pin. So for that pin configuration. Then, as I told, this we will be generating through timer interrupt. So you need to initialize the timer. Okay. So to initialize the timer, I have used this function. And the content of the function, here it is elaborated. So first is the status register. Already you know about the status register. The ith bit or the 7th bit of the status register define the global interrupt enable. Whenever you want to work with any interrupt, so definitely the 7th bit of that status register to be made high. So that's why it is written as 1. You see, here it is 1. Now we are using here timer 1. Timer 1. So TCNT1 That is the data register for the timer 1. So what I did here, that I initialized as 0. Always it is better to, while you are starting the timer, better to initialize it. So that's why the data register I made as 0. Then here I have used 3 more register. This TCCR1A. So let us see what is this TCCR1A. You see, this is the TCCR1A. And here, what I did, now we'll see what are the bit. First, I will come this 4-bit. 4 MSB. So first, that is 1110. That means these two, 7th and 6th bit are 11. What it is significant? So you can see here. This is the PWM mode. And I have used the phase correct PWM mode. We will elaborate it. So here 11 signifies that the output compare pin, it will be set while match and when it is up counting, and clear while down counting. What is that? Let us understand it. In phase correct mode, the timer will go from its initial value to maximum, then again maximum to minimum. Like that way it will go. This is called your phase correct mode. Okay. But in another mode is there, which is called fast PWM. In fast PWM, it will go from the initial value to maximum. Again, immediately it will come to, suddenly it will come to initial value, not in that slope. It will sharply fall. Perpendicularly, it will fall. That is called fast PWM. So here, whenever we will be working for power electronics application, so there we need phase correct mode because we need to provide the dead time. That also we will learn now. So this process is called up counting and this process is called down counting. So now say your output compare register value is somewhere here. So what will happen? Some up counting match here occurred. So your pulse will become high here and keep on high. And when it is match while down counting, it will reset like this. Similarly, say here the compare register value is this one. Then what will happen? Here it will match. Then it will go high. Keep on. Then here it will fall like this. So this is this is called phase correct mode. And as I said, that particular channel 11. So basically this pulse is called non-inverting PWM. Non-inverting PWM. Now for the complement, you know, there is a things called complementary pulse in power electronics application. So that means you need the inverted pulse. So for that, you see, if I set that particular bit 10, what will happen? Clear when up counting and set when down counting. What is mean? What it's mean? Say now my output compare register is somewhere here. So now, or this things is somewhere here. So what will happen? How the pulse is? So this is up counting. What I told? Up counting is clear. Okay. So say earlier the pulse was high. So here it will be clear. And down counting, it will be set. So down counting match will here. So it will set. You see, just you are getting the opposite kind of pulse. Inverted pulse. So this pulse is called inverted PWM. And now you know, if these two pulses are going to a complementary switch, those two pulses should not be, the transition should not occur at the same time. So we need some gap. You see, this is that gap. This thing is called in power electronics as dead time. So you have to see the switch specification and how much the dead time is required for that particular switch. Based on that, you can reduce the value of the output compare register. So now this 4-bit application we have understood. Now let us see what are the other 4 bits. You see, this other 2 and 3 and 2 bits, that is nothing is there. It is a don't care condition. And this 1 and 0th bit, it is WGM 11 and WGM 10. So this is called waveform generation mode. And you see, this is the waveform generation mode. So in waveform generation mode, we are selecting mode 3. So that is phase correct resolution with 10 bit. So that's why these 2 bits means WGM 11 and WGM 10 should be 11 and WGM 13 and WGM 12, that should be 00. So that's why you see, I have written these 2 bits as this. Okay. So the explanation for TCCR1A, it is clear. Now another register is there, the TCCR1B. So what is that register? So this is, you see, this is TCCR1B. And you know, this WGM 13 and 12 of that waveform generation mode, these 2 bits are in register B, but that is 0. So that's why, and we are not using this ICNC1 and ICES1. So that's why all these things, it will be 0. Then what is these 3 bits? These 3 bits are called prescaler, clock prescaler. Say you need to change the PWM. You need to change the PWM frequency based on, because it will, the crystal is say 16 megahertz or 8 megahertz, something like that. But if you generate the PWM is very high speed, so your switch having a limitation of its switching, it cannot go more than that. So you have to reduce the effective clock of the timer. So that time you need to change it. So for that purpose, these 3 bits are there. So if it is 0, 0, 0, no clock will be, means timer is off. If 0, 0, 1, without any prescaling, it will be coming. So now you see this bit I use 0, 0, 1. That means at present there is no prescaler. Okay. So now how to decide the PWM frequency? So if you read properly in the PWM part, so there the PWM frequency, how to calculate in the data sheet, it is given in a very detailed manner. Now you see, this is the phase correct and the frequency correct mode PWM. So what should be that? Clock divided by 2 into n. N is the prescaler by top value. So here top value is what? You see from the waveform generation register, we have selected the mode 3. So mode 3 means it is 10-bit resolution. 10-bit means it is 1024. So our clock is, and here prescaler, we selected as 001. So that means 1. So now, what should be the PWM frequency? So this is our crystal is 16 megahertz divided by 2 divided by the prescaler divided by the top value, which is 10-bit resolution, is this one. So you will get this frequency of the PWM will be 7.8125 kilohertz. This is a simple calculation for the PWM frequency. Now another register I have used, this TIMSK1, and that the 0th bit I have set as 1. So let us see why I have done this. So that is TIMSK1. You see, this is the TIOE. What is that bit? You see, this bit is called overflow interrupt. So once the timer full counting is over, it will generate one interrupt. As I told, it will count from 0 to maximum and then maximum to 0. Once this process is over, this microcontroller will generate one interrupt. Okay. So for that, to enable that overflow, which is called timer overflow, timer counting is over. So to initiate that, I have enabled the timer overflow interrupt. Okay. Now you see, once the overflow is occurred, then I need to put the duty cycle. So that time it will redirect to this ISR, means the interrupt service routine. It will go to this interrupt service routine, and here only I am putting this duty cycle 300 and 300. Simple. Okay. So this is all about the code. It's very simple. This is the header file. Then this is the initialization. And this is the output pin declaration and the timer configuration. And this is the simple interrupt service routine where I have defined the duty cycle. So let us compile it. You see, the compiling is over. So now I'll open the simulation file. And here, if I enlarge, Now you see, I have connected because the timer one, see the CRO is connected with this. You can remember in pin configuration, I have defined PB1 and PB2 as output. And here, you see, this is basically the output compare register channel A and channel B. There only these things will connect. Okay. So one will give non-inverting PWM, another will give inverting PWM. With the, so now I will go to that. So this is our code. Now we'll run it. Now we will change the time period. And you see, so our duty cycle was, so our total resolution is 10 bit. So it is 300 given. So it's just around 30%. So you see the blue pulse is giving the non-inverting pulse, and the yellow pulse is giving the inverting pulse. But here, if you see, now, if I match these two like this, then we'll go slightly and we'll increase the amplitude also. Here you see what is happening. If you see the transition of the both pulses are in the same time, the pulses are toggling. On that period, if you are giving these two pulses in a complementary switch, what will happen? For that instant, the DC source will get short. It should not happen. So how to avoid that? For that, we need to give the dead time. So now here I am doing around, so this pulse I am giving now around 50%. So 512. And that pulse B, I am reducing it. Say I am giving it 450. How much count it is to be reduced based on the dead time of the switch? That calculation already I have shown how to calculate the PWM frequency. So from the PWM frequency, you can find out the time period. And this time period will elapsed after this counting, means counter once it is going from 0 to 1024, because it's a 10-bit resolution. In that period, it will, in that counting, during that counting, it will elapse that much time period. So from there, you can find out what is your dead time. And for that particular dead time, how much count is to be reduced. So for here, arbitrarily, I reduced, it is 512 and it is 450. So let us see what will happen in this case. Now you see, here it is very clear. You see, once the yellow pulse toggled from high to low, and when the blue pulse is toggling from low to high, in between there is some gap. So there is no question that the both switches can short. Both the switches can on at same time. So this concept is called generation of dead time, which is very, very important in power electronics application. Say you are going to make one 4-quadrant DC to DC chopper. So that time you need the complementary pulses. And when you are dealing, we'll be dealing with complementary pulses. So you should be very careful that for any instant, both the switches should not be on together. So this is the very fundamental concept to generate dead time for the complementary pulse. So hope you have understood this code. Now we will go for the second code, that is sine PWM generation. So here only one difference. For sine PWM generation, I have made one array. So this array calculation, it's a simple trigonometric calculation. I am not going to tell all these things, that, or I will very quickly I will tell. Now you see, what is your PWM frequency? This one. Now what is my power frequency, which I want to generate? That is 50 Hertz. So the 50 Hertz can be made with this PWM pulse. Then how many PWM pulse is required so that the 20 millisecond will cover? It is very simple. You divide it by 50 Hertz. So it is around 156. So this 360 degree is divided by 156. That means in this array, 156 sine element is there. Okay. That means what it's mean, I is equal to 0. Okay. Then your sine theta, that means say that value is A, is equal to sine (360) divided by 156 into I. And once this I going more than 156, what you are doing? You again starting the counting from 0. Getting? So first it will start from 0. It will give sine 0. Then here it is I plus plus. I will be getting incremented. And once this I become 156, so 360 degrees over, then immediately it will initialize. If it is I crossing the value 156, again I becomes 0. So these things only I am doing. Nothing else. It is same as the earlier code. But only thing, in earlier code, our duty cycle was fixed. But here, at every PWM cycle, the duty cycle will be updated, which is a function of sine theta. That is called sine PWM. Okay. All other things are same. And here you see, for the complementary pulse, what I did, you see, for non-inverting pulse, I have given the exact value. Here, why these things are done? 500 into 1 plus AI, because sine theta will be negative. But your value of the output compare register cannot become negative. No? It will it will fluctuate from 0 to 1024. So that's why I am dividing by 2, means I am giving a, you can tell it's I am giving a DC shift. For that only this is written. So basically this is 1 plus sine theta into resolution by 2. That only I am doing. Okay. And for the complementary pulse, here this is your dead time. I am reducing 80. But sometime what will happen, as it's a function of sine theta. So sometime the value will go beyond 80. Sorry, below 80. And below 80 value, if you minus 80, then what will happen? It will go negative. But negative means microcontroller will give garbage value. So that's why I am settling that value. If it is greater than 0, then I am that duty cycle will be as per this. But if it is less than 0, then I am restricting it to 0. I am not allowing it to go to negative. Okay. So this is this will and this. And what is this AI? This AI is nothing but the sine theta taking from this array. This is called sine PWM. Okay. So now if I compile it, so once again I will show the program slowly. So this is the sine theta. So based on my PWM frequency, how many sine elements are required, that I have calculated, which is nothing but the PWM frequency divided by the power frequency. So I have to divide 360° into that many segment, and it will be incremented, and the sine theta is written here. Then these are the same thing. We are configuring the particular pin as output, as well as the timer configuration. So this timer configuration is same as earlier. One, it will be giving inverting, and another it will be giving non-inverting PWM. Here what I am doing, because we need a dead time, so the dead time here I have defined, I am reducing the count 80. It's arbitrarily, but while you will be doing, you should calculate, and based on that you have to put. But as the duty cycle is a function of sine theta, so sometime it will go less than 80, and that time the value will be negative, which is to be avoided. So till the value is greater than 0, so I am using this formula. At once this value going less than 0, I am restricting it as 0. And that only I am giving the duty cycle of the complementary pulse. This is the simple thing. Now you see, who are familiar with sine PWM, they can understand. This is the sine PWM. If you give these two pulse to a H bridge, the complementary switches, at the output you will get the 50 Hertz AC signal. And you can check whether for any instant, both pulses are overlapping or not. Some 2-3 instant we will pause. You see, there is a significant gap in between. Both the switches is not on together. Here also you see nothing. Here also you see the significant gap is there. So while we will be doing, so this, I think one group of students, they are working in renewable energy lab. So if you want to see these things in practical way, how the protection is given, because sometimes your things can malfunction, a driver circuit can give something. So what basically provided as protection, that these two pulses will be taken to a AND gate. And if both the pulses are on together, then AND gate will give a high output. That means otherwise every time AND gate output will be 0. But at once, this AND gate output is high. That output will be taken to the external hardware interrupt pin of the microcontroller. And once this raising has occurred, immediately you should off the timer. Off the timer means you make that clock bit 000. Again, you need to reset. So your switch will not damage. So this is the practical protection is provided in microcontroller to avoid the damage of the switches due to complementary pulses. So these two things are very important. There are several things are there. I am restricting this course content because this is the last lecture of this series. Somewhere you need to generate very high frequency PWM. So basically some friend or maybe some seniors, they are generating, I think, around, Sridhar sir is developing one induction heating through solar application. So they are, I think, based on the L and C parameter of the coil, you need 25 kilohertz PWM for the occurrence of resonance. So they have made it. I think they have tested. That is another technique, because here, if you use whatever the procedure I told, there are some fixed value PWM only you can make using that waveform generation register, because there is a distinct charter there. But if you want a certain value of the certain PWM frequency, anything. So for that, this technique is not sufficient enough. For that, you have to use another register called input capture register, ICR. So with that only I taught them, because that PWM frequency needed always customized in case of resonance. So they have done. So if you want to see, anytime you can go to second floor, renewable energy lab, and you can see the physical output. These are the simulation. You can see physically. So this was all about today's lecture. So I don't know how much you have understood. Now you can ask If any question is there, you can ask, or otherwise I will terminate the session. Thank you so much.
So this is Jagdish. I will assist you instead of Geeta ma'am. Okay. Students, do you have any questions? Feel free to raise the questions one by one.